Hi, so let's start with a new experiment today, and the experiment is to find the resistivity, and with the help of this resistivity we are going to calculate the energy band gap, the band gap of the given material, and we are going to find this by varying the temperature, okay, and calculating the resistivity. All right, so the aim of the experiment is to measure the resistivity of a semiconductor with temperature and to determine its band gap. Fine. So what are the apparatus that you require? You require a 4-probe setup. I'll tell you what these things are. Then you need some semiconductor chip, which we will give you, not necessarily semiconductor, even you can use it for metals also, and a constant current source or low current source, anyone as per your requirement. Digital voltmeter you'll require, and you need a PID controlled oven, okay, where PID is a technical term used for some a very good digitally controlled instrument, so we need not be so much bothered about the full form. Okay, so the formulas that would be involved or required is corrected resistivity, which will be the resistivity that you have calculated. You'll be calculating some resistivity, you'll get it, and you will have to get the corrected resistivity, which is nothing but the resistivity divided by the correction factor. So this comes in because the chip that you will be using is very thin chip. As you can see, thickness of the chip is just 0.5 mm. Okay, so it's going to be very thin chip, so there are a lot of errors in it, so you need to, and also on one side it is coated with a non-conducting material and all that. So putting into account all this, there is a correction factor which is given by the instrument, the one who supplies the instrument, and it is given as 5.89. okay, the formula is G7WS, where G7 is given by the company that supplies you the instrument. W is the thickness of the chip, and S is the probe distance. I will tell you what is probe distance when I show you the image of the probes. And the resistivity formula, and that is here, is which you will be calculated, will be voltage upon current multiplied by 2 pi S, where S is the probe distance again. And once you get the resistivity, it's very easy to find the energy band gap. Energy band gap is equal to 2K, where K is the Boltzmann constant, and you're supposed to use this value of Boltzmann constant only, that is 8.6 into 10 raised to negative 5 electron volt per Kelvin. There is another value of Boltzmann constant which is in joules, so we don't want the one in joules, we want the one in electron volt. So be very careful, you have to use this Boltzmann constant only, that is 8.6 into 10 raised to negative 5, because we want energy band gap in electron volts. Then 2.303 is here because this log term is in the theory is log of E. So when you convert it, the log of E to log the base 10, you need to multiply it with 2.303 log 10, and rho is your resistivity that you have found. Okay, the corrected resistivity term that will come here, and 1 upon the temperature, as you are going to vary the temperature to measure the energy band gap. All right. Principle is very simple. Okay, the 4 probes are placed on the flat surface of the material to be measured. So these are the 4 probes. I'll show you the actual diagram also. So the material is placed just below these 4 probes. As you can see, thin pins of these probes will be touching the material. Okay, and you can see each of the probes are connected to, like this, the outermost probes are connected to a current source which can be in nanoammeters or milliammeters. We are using milliammeters. And the inner 2 probes, one is connected to the potentiometer, other one is connected to the microvoltmeter. Okay, so in that way, and all right, so this is this, and each of them are separated by equal distances. S1, S2, S3 are all equal to each other. Okay, and but most important thing to remember is the outermost probes are connected to current source, and inner 2 probes are connected to the voltage source. Okay, so the 4 probes are placed on a flat surface. The current is passed through the 2 outer electrodes, the same thing that I said, and if the flat surface on which the probe rests is adequately large, it may be considered to be a semi-infinite volume, very obvious. And to prevent minority carrier injection and to make good contact, the surface on which the probe rests may be mechanically lapped. Now what is meant by mechanically lapped is that the coating, the top surface of the chip that is given to you, you may just in our case we can just rub it or clean it with emery powder. Okay, lapping is not required, but if you are making your own sample, then you will have to lap it. You'll need a lapping machine on which you will have to stick your sample, and you will have to polish it completely, okay, till it gets a very uniform surface. Okay, otherwise readings will be very wrong. So here in the chips that is given to us by the manufacturer is already lapped. We don't have to do the lapping, but since it is kept unused for a very long time, there will be a coat that is formed on top of it, which can be simply cleaned with the help of a alcohol, isopropyl alcohol maybe, or alcohol and emery powder. You can just rub it on the surface and it will then get cleaned. You'll get a very shiny surface. Okay, so that's about the principle. So there we have given by the manufacturers, we have a sample, a chip by silicon. We also have a chip by germanium, also we have aluminum foil given to us. What we are using in this experiment today is a germanium chip. As you can see, when I took the photograph, this I had cleaned, actually I had performed a sample experiment using this silicon crystal. You can see the surface is so clean, and when I took the photograph of the germanium, it was a little bit dull here because I had not used this. But while performing this experiment for you all, I have used germanium crystal and I have cleaned it, and the surface was the way it can be seen here, okay, of the silicon. So like that kind of a coating, okay, we need not do the lapping. Lapping is already done by the manufacturer. We have to only just clean it nicely. All right. So the entire setup looks like this, as you can see here. Okay. So what all we have? We have the this is the instrument that will sense the temperature. This is the furnace that is given to you, and this is the digital PID controlled oven, okay, which will show you the display about what is the temperature. The top reading is the temperature what is there present right now, and the down reading, the green one, is the set temperature. We are going up to 150 degrees Celsius, therefore I have set it to almost 170 degrees Celsius, okay, a little bit higher than the reading that you will be taking. Also you can see on this you have two modes, one going towards up to 200, otherwise you can shift it so that this oven which is given to you can go up to 600. Okay, since we'll be going only up to 150, we'll be selecting an oven which will be 200 degrees Celsius. Okay, there are two buttons here, on buttons on this. Also there is one more button right at the corner here to switch on the entire instrument here which is given to you. Fine. Okay, and of course they are all connected to this furnace that is given to you. So how to change this? There is three buttons, one here. This button will help you to toggle between the three digits, the digit that you want to change, and then this button is up and down button. The up button obviously to increase the value, and down button to decrease the value. Once your value is set, the value, that maximum value that you want to go up to, after that you need to press this knob which is called MD. Okay, there's an MD knob, you can just put on that, and after that you put on the oven. Okay, once all this is done, after that you can put on the oven. Fine. Okay, so I hope this is understood how to set a oven, but you don't have to worry, we will keep it all set, but as a experiment idea you need to know what all things are happening. So let me just get rid of all this. All right, next what you have is the furnace itself. Okay, you can see this is the crystal will be, this is a holder for the crystal and the 4 probes inside. I'll show you how the 4 probe looks like in my next slide. Okay, but entire setup is here, and the entire setup goes into the oven, and this is the oven which can go up to 600 for you. Okay, so once it is hot, do not touch this oven, it will be very hot. Even the experiment that you are doing is up to 150 degrees Celsius, which is also very hot. Okay, so do not see that you keep your hands away from this oven when you're working on it, and once your experiment is also over, don't touch it, just be away from it. Fine. Also before starting the experiment, see that the temperature is around room temperature. Okay, otherwise don't start the experiment. Okay, and once the experiment is over, just leave it as it is. We will take out the crystal if it has to be taken out. Okay, so you don't bother about it. Next that we have is a constant current source. It can be shifted to 20 milliamps to 200 milliamps. Okay, while conducting the experiment, I have shifted to 20 milliamps because max that I have gone is 5 milliamps. Okay, so and this is the controller that just to increase or decrease the current. Okay, so obviously you will also have to keep it on 20 milliamps. Next that we have is a digital micro voltmeter. Okay, so we have taken readings on voltages, so I have set it to 2 volts, or 2 volts or 20 volts. We'll see while doing the experiment, because we are taking readings in voltages. Fine. And next up what we have is the low current source, which we are not using in today's experiment that we are doing. We are only using this current source. We are not using the low current source. Low current source, you can see, goes to 2 microamps up to 2 milliamps, but since we had to set the current up to 5 milliamps, we didn't use this. Okay, we are using only the lower ones. Fine. So the setup, all the meters have been kept like this, one above the other. Okay, when you will see it in the lab, it will be looking like this. And the 4 probes, I have taken a close photograph, as you can see, is let me use a magnifying. Magnifier is here. You can see I had cleaned the germanium crystal, very clean it is, and you can see how the probes are kept, and the distance between the 2 probes, as it is told, is 2 mm, I think it was told. Okay, so that is the distance. It is a fixed distance by the manufacturer. You don't have to do any changes, but do not press it, because there is a spring here on top of every probe, and you are not supposed to press this too hard. Just see that it touches the crystal and then stop it. Okay, at that point you are supposed to stop. Just touch it. Okay, just very finely touch. That's enough. All right, so we are done with the explanation of what is to be done in the lab now. So let's go to the lab and perform this experiment, and I see you soon after doing the first step. Okay, and then we will again continue with the second step. Okay, so see you after the first step of experiment. Hi, so we have all now looked in the first session about how, all the apparatus that we will be using, and why or how the 4 probe actually helps us to get the resistivity and the band gap. Okay, so we have 2 parts in this experiment. One is to find the resistivity, and second is to find the band gap. Okay, so one is to find the resistivity of the material. So we are going to choose germanium chip. Okay, so we have 3 options, as I told you already. One is aluminum, silicon, and germanium. I am using the germanium one. Okay, here, and the germanium chip has been cleaned and is already placed in the 4 probe here. And when you're placing the 4 probe, be very extremely careful. Okay, because slight if you place it very harsh or very roughly, then chances are that you will get the readings over here might change because of that vibrations, a harsh vibration that will happen while placing. So place it very carefully inside the furnace. So this is a small furnace which can go up to almost 600 degrees Celsius, but we will be taking reading only up to 150 degrees Celsius and not much. Okay, so as I told you, this is a low current source, may not be of use in the germanium diode chip, not diode. We are using the chip, so may not be of use. So we are using the digital voltmeter. Okay, which has, I've explained you all these parameters already, so I won't go in detail. So but while I'll place it, so actually the current is almost nil here. Okay, or if you find something like this, if you find some extra current, okay, then it may be because the probes are not placed so perfectly. So what we do is we just take it out, and after that you can just simply loosen it a bit and pull it up. You'll see the current becomes 0. Okay, so now while placing it, place very slowly, and moment it touches the chip, okay, so some sort of an excess 0.01, 0.02 milliamp of current has been detected. Okay, but it's fine, no problem. So since we tried it once again, so since it is showing, so that is an excess little bit of error current that we are getting in the milliamps. Okay, so otherwise current is 0. Fine. Okay, so what do we do is just hold on for some time and then adjust. There's a zero adjust knob here, so we use that to make this voltage 0. Okay, so adjust it slightly till your voltage becomes 0. Just change the knob to milliamps and check. Okay, so looks like that's the smallest error that we will have to face all the time. So it's fine, so we can just continue with it. No problem. With the zero adjust also, it's not becoming 0. Yeah, so just leave it. Maybe I can just give some current and check. It's working fine. It's working fine. Okay, so it is a very small current. We are getting some small voltage which is not getting adjusted with zero adjust. It's fine. Okay, but otherwise when I was practicing, the zero adjust was giving 0. Okay, it's not happening now, so let's not waste time on that. It's fine because the addition that you're getting is a very small one, 0.003. So first part, as I told you, is to find the resistivity, and in resistivity what you need is to find, give some current here. The current that we will give is 0.5 milliamps, 1 milliamp, 1.5 milliamp and 2 milliamps. Okay, and note down the voltage. 4 readings are enough. Okay, and just note down the 4 voltages and then find the ratio of V by I. Okay, and then we will find the resistivity from it. And the second part is to vary the temperature. Okay, it's almost 12 o'clock now on my watch, and temperature that it is showing is around 34 degrees Celsius, which is a bit higher. Maybe that is the temperature. Okay, but so moving on, so we can first start, give some current 0.5 milliamps. So there it is, 0.41. It became too much. Just give 0.5 milliamps. Okay, so for 0.5 milliamps it is 0.047 and the knob is on the 2 volt, so it is voltage reading that we are getting. So we'll just note it down that for 0.5 milliamps, yeah, it is 0.047. Okay, 0.047. So I think that's also clear in your display there. Let's increase it to 1 milliamps, the next reading. So it's 0.9796. Try your best to get very close to 1 milliamp, that is 0.99, 0.98. Okay, I think we should take this reading for 1 milliamp because anything that we touch, it becomes either very less or more. So this is, let me take this for 1 milliamps. Let me note it down as 1.01. No problem. Okay, it became 1 milliamp, no problem. So now we can write it down as 0.095. Okay, so we can write down this as 0.095. Okay, 0.095. So that's our 1 milliamp reading. Let's move to 1.5. Be very slow, very sensitive instrument. So this is 1.5. I think we can take this, okay, little bit. Yeah, so I'll take this reading. I'll just note it down that it was 1.48 rather. Okay, because if I adjust too much, then the reading goes, since it's too sensitive. Okay, so yeah, so 1.5. So we'll take this up because adjusting 1.5 is coming a little complicated. So I go for 1.48, the closest that I can go. I will take that. So the closest I could go is 1.48. Anything more or less is coming, it's going out of 1.5. So let me take 1.7, 1.48. Let me also note it down that it is 1.48 here, and the reading is 0.139 is the voltage. Okay, let me note down 5 Simon. Let's go to 2 milliamps. Okay, so 1.9, 1.98, yeah, 1.99. So let's note down this one. It's 0.186 for 2 milliamps. Okay, so now before we go to the second part of this experiment, let's go back, do the calculation for resistivity, and then come back Okay, let's do the calculation for resistivity and come back for the second part where we vary the temperature and note down the voltages. Okay, so see you for the second part. All right, so we are done with the first step. So let us now just do quick calculations of the first step, that is to calculate the corrected resistivity. As you saw, we had got for different currents 0.51, 1.52. The voltages were as shown here. These are the same voltages that I've taken, and the V by I, then the mean, and just put this in this formula. As you have seen, V upon I 2 pi S, where S was 0.2, and this is the resistivity that we got. You can see it's quite high, and that's why we use this corrected factor or correction factor that we use, and therefore we get the corrected resistivity, which is 19.98 ohm centimeter, which is a very good value, okay. But this is not the most important thing, so we need to go back and continue with our experiment to get the energy band gap. So see you again. So now that we have done calculation for resistivity, let us move to the second part, that is to find the calculation or find the energy band gap of germanium chip that we have used here. Fine, okay. So what we do is now we keep the voltage, constant voltage we give now, okay, of 5 milliamps, and that I mean to say current, okay, constant current of 5 milliamps we will be giving, and we'll be varying the temperature from 35 to almost 150 degrees Celsius, okay, up to 150 degrees Celsius we will go, and note down the variation in the voltage, but in that we have to see that the current remains constant at 5 milliamps, okay. So let's increase it, let's increase to 5 milliamps. In fact, you can keep any constant value. 5 milliamps is most prescribed one. You can actually go for even 7, okay, 8, no problem, okay. So see that this remains constant now, 5 milliamps. All right, so it says on 20 milliamps, so now 5. Let's go very close to 5 milliamp. Why is the current decreasing? Okay, there we have set it to 4.99, the closest that we could go. For some reason the 5, it's not getting stable, so 4.99, and I can say it's 4.98, but that's fine. So we keep the current constant up to there's a current that will give I will be equal to I'll note it down as 5 milliamps only, okay. And what we'll do is now start increasing the temperature, okay. And as now we can see the temperature is set to up to 50 degrees Celsius. All right, so temperature is set to 50 degrees Celsius. So what I do is I will just, there are some knobs here which I will use and increase the temperature to 170. Okay, I will increase the temperature to 170, which will be the upper limit, okay, which will be the upper limit of this temperature, okay. And as I'm starting the readings, the first reading that I'm getting is up to 36 degrees Celsius. I don't know what has caused the rise in the temperature here, but it is 36 degrees Celsius. And I will note down the voltage for 36 degrees Celsius. And also one more thing to note down is the temperature is degrees Celsius, we will have to convert it into kelvins, okay. So for 36 degrees Celsius the voltage is 0.464, and now I put on my oven so that it's the heating starts, and I will take reading at every 10 degrees Celsius, okay. So the next reading that I'll take is at 40, and then after that I will start taking reading at every 10 degree rise in the temperature, okay. So what I'll be noting down is the voltage, okay, so which is already 0.464 for 36 degrees Celsius, and then next reading that I have to take up is at 40 degrees, okay. So now we'll wait till the temperature becomes 40 degrees. So now the temperature has reached 40 degrees Celsius, and I'm noting down the voltage, and the voltage is 0.442, 0.442 when I first saw it. Now we wait till the temperature becomes 50 degrees Celsius. Okay, now the temperature has reached 50 degrees Celsius. Again, we note down the voltage for 0.379. Okay, it's 60 degrees Celsius now, and it is 0.302. Let's move now for the 70 degrees Celsius. So now it's 70 degrees Celsius and the reading is 0.230. Okay, it's 80 degrees Celsius and now the reading is 1.169. Now it's a 90 degrees Celsius and reading is 0.127. Okay, so we are about to approach 100 degrees Celsius. So now it's 100 degrees Celsius, 0.095. 095. So we are now on 110 degrees Celsius, is 0.070. It's 120 degrees Celsius and 0.05053 is the reading for 120 degrees Celsius. And we are left with 3 more readings. So we have reached to 130 degrees Celsius and it's 0.04. So it's 140 degrees Celsius, reading is 0.031. Okay, so we are on the last reading now, 150, and it is 0.024. So with this, we have finished taking the readings for the part 2. Okay, so immediately after that, see that you switch off the oven. Okay, the oven you have to switch off. Okay, and let the furnace be on so that we know what is the temperature. Don't by any chance touch the furnace. It's going to be hot, very hot, 150 degrees Celsius it is around. So don't even touch it. Don't try to remove anything, nothing. You'll get shocked because of the high temperature. Okay, then don't blame us. Fine. So switch off the oven. Just keep this on so that we know at what temperature is running, so that after almost 50 degrees and below we can remove the chip out from the furnace. So you don't bother about it. About this one, just bring the current back to 0. Okay, and switch off the constant current source and also switch off the digital microvoltmeter for you. Okay, so you see for this particular one, the germanium one, we did not need the low current source. Okay, it could be needed for the aluminum or silicon chip if required. Okay, so we are working on the germanium chips. So and also for exams we will give you germanium chip also. Even if some other chip is given, don't worry, the procedure is same. Fine. So now let's go back and calculate the energy band gap that we had to calculate and check and compare both the resistivity that we have already calculated and the energy band gap to that of the known values of germanium. Fine. So see you for the calculation in the next section. So welcome back to the last steps. So we have kept the current constant to 5 milliamps, correct? And we had increased the temperature from 36. For some reason the room temperature was 36 degrees Celsius, and we took it up to 150 degrees Celsius, convert them to kelvins, you can see here, and then the voltages that we noted down is same voltages that I've taken up here. And the resistivity, I've done little changes in the formula. Little changes means I've just used all that what was known and just made a very simple formula to calculate the resistivity, as you can see here. Okay, so this was the formula that was given to you, correct? And then these values are known, 2 pi s is known, so we use that. And then we use this resistance, corrected resistance, rho naught, and the 5.989 which is there, and current is kept 5 milliamps. So you can just divide 1.256 by 5 milliamps, so 5 into 10 raised to minus 3, and then you will get the entire corrected resistivity as 42.6 into voltage. So this resistivity, the corrected resistivity that I'm getting now, is simply multiplying this 42.6 with every voltage that I'm getting here, and this is the corrected resistivity that I'll get. Then temperature, we have to find the inverse, the Kelvin one, we have to find the inverse of it, into 10 raised to minus 3 we'll get every time, and the log of the rho to the base 10 we are getting here. Okay, so once we have got all these value, next what we need to do is plot a graph. All right, so start plotting the graph, and once you have used the computer, also on your graph paper it will come the same way. All right, same to same. With free hand you can try to join the points. As you can see, these points are come almost very straight, and it is then bending upwards, which is expected. And the slope that I have calculated comes to around 1041.17. all right, and use that in my formula for energy band gap, 2k, and k value is 8.6 into 10 raised to negative 5, and the slope value that I found I'm using here, and I found that the energy band gap is 0.76 electron volts. The perfect value is 0.68 electron volts. I think we have got good value. For some reason, some values were fluctuating as we were doing the experiment. Otherwise, we would have definitely got much closer than what we have got. Okay, this is also not bad. Very good reading for a germanium crystal. Fine. So what are the results? The results, first thing, yes, temperature dependence we saw. Okay, we saw the temperature dependence, perfect, and the energy band gap of the given semiconductor is 0.76 electron volts. So we are done with this experiment. Okay, so I hope you have liked this experiment. It's quite easy. It would take around 1 hour for you to completely finish this experiment, or at the most 1.5 hours for you to finish this experiment. Okay, so thank you, and we'll see you for the next experiment.